Alright, welcome to 1.13. This is the last lesson of Unit 1, so we're almost there. The last thing that we're going to look at is actually something that we're also going to look at the beginning of Unit 2, and this is a way of categorizing functions in a way that is really useful, particularly when we get to calculus and we're trying to do a lot of complicated and lengthy different observations. This will really help us tremendously to make sense of situations. So it's a really good skill to have. You can ask any of the calc students currently in about a month or so, and they will tell you that even and odd functions have been really helpful. So now you can go ahead and discover what an even and an odd function are by looking at some examples and some non-examples. And from those you'll be able to determine some of the key characteristics about what makes a function even and what makes it odd. So go ahead and copy these graphs and these labels into your notebook. Let me just be super clear on what you're going to need. You're going to need obviously the labels and the actual function itself. For the graph, just make sure you have the x and y axes, I guess x and y axis, and then that you have the graph and that it looks just like it does here relative to the x and the y axis. You don't have to actually have the values here and count these out. That's not going to be necessary. Okay? So go ahead and decide what makes a function even, what makes a function odd. I promise that you'll be able to get fairly close, just commonsensically, what makes an even and an odd function even and odd. Alright, let's first take a look at even functions. And if I look at the hint here, it said, look at the degree of the equation and the symmetry of the graphs. Well, I like to go visual first, so let's take a look at the symmetry here. What symmetry do we notice? Is it symmetric about the x-axis? Well, no. Above the x-axis looks a little different than below the x-axis. What about this? It looks like this part is similar to this part. And in fact, they are, right? They're symmetric about the y-axis. If I were to flip the left side of the y-axis over the y-axis, I would end up with exactly what I have over to the right. That's the definition of symmetry. So my line of symmetry is the y-axis. Well, let's take a look at the not even function. Clearly, the symmetry, there's none here, right? Certainly, there's no symmetry about the y-axis, right? If I were to reflect the left side of my function over the y-axis, I would definitely not get what I have on the right. And so we notice here that an even function seems to be symmetric about the y-axis. Now let's take a look at these values here, and notice that all of these are even degree functions. So this is x to the 6th, x to the 4th, x squared. What happens when you have an even degree? Well, that means you're multiplying the number an even number of times. And while we haven't talked about this in great detail, even when you plug in, so if you have x to the 6th, if you plug in a positive number and you plug in a negative number, if they're the same absolute value, like for example negative 2 and positive 2, you're going to end up with the same answer because it's an even degree. And this is essentially what this is saying, right? If you have even degrees, you're going to end up with the same thing on the right hand and the left hand side of the y-axis, because these are positive x values and these are negative x values. And it doesn't matter whether we have a positive x value or a negative x value. If we raise it to an even degree, we're going to be in good shape. It's going to be exactly the same. However, notice here we have some odd degree terms. We have x to the 1 and x cubed. Well, think about x cubed. If you put in a positive value for x, you're going to get a positive value back. But if you put in a negative value, you're going to get a negative value back. And so clearly, the values to the right and left of the y-axis are not going to be the same. Now let's take a look at odd functions. So this one is a little bit trickier to see, but I think based on what we saw with the even functions, you'll be able to get it. So let's take a look at the symmetry. What kind of symmetry do we notice here? Well, it's not symmetric about the y-axis, certainly. Is it symmetric about the x-axis? Well, not quite, right? If I flip it over the x-axis, notice that it's reversed, right? So like this peak here will be up here now, and this peak here will be down here, so not quite. So maybe not think about reflections, what could we do and to notice some symmetry here? Think about this. What if you took this piece here and you turned it 180 degrees? So you pinned down the origin and you rotated 180 degrees. Well, now all of a sudden you'd have the exact same function, right? This peak here would end up rotating and becoming this valley down here. And this valley down here would rotate 180 degrees and become this peak up here. And in fact, that is what it means to be an odd function. And let's look now at the not odd function and notice that you can't do that, right? If I were to rotate about the origin, this peak here would all of a sudden become a valley over here, and it wouldn't work. So we notice that an odd function has the symmetry that if you rotate 180 degrees around the origin, your function will be in the exact same position. Let's try and nail this down a little more concretely by taking a look at the odd polynomial terms here. So notice that all the degrees of these terms are odd, 1, 3, and 5. And remember, with even functions, because we had even degrees, when we plugged in a positive value for x and a negative value for x, we got the exact same answers. Well, what will happen here if we consider an odd degree? So let's imagine you have x to the third and you plug in a positive number. Well, you're going to get a positive value back. So for example, if you plug in positive 2, 2 cubed is 2 times 2 times 2, or 8. Well, what happens if you plug in the opposite value, negative 2? Well, negative 2 times negative 2 times negative 2, that's 4 times negative 2, which is negative 8. And so you actually end up getting the opposite answer. And you can kind of see how this makes sense, right? So if I plug in 2, I get some positive value. If I plug in negative 2, I get the exact same value except negative. And that's the characteristic that odd functions have. Okay, so let's go ahead and define these more concretely so that we can actually find out for sure how to prove whether a function is even or odd. All right, so classifying functions. Functions can be even, odd, or neither, and when they're even or odd, they really help us out because we can kind of define things in a certain way, and you'll see that when you get to calculus. But now we want to focus on how can we show that a function is even and how can we show that it's odd. So we'll look to the definition. A function is even when the function f of x, so evaluated at the value x, is equal to the function when you plug in negative x. So notice that x and negative x are opposites of each other, right? So this is essentially saying, hey, if you plug in some value to your function, it's exactly the same as when you plug in the opposite of that value for all x values. In other words, there is symmetry about the y-axis. Right? This is just saying if you plug in an x value, when you plug in the exact opposite on the other side of the y-axis, you get the same value. So that's where you get the symmetry from. An odd function is odd when negative f of x is equal to f of negative x. Well, think about what that means. Remember when we plugged in 2 to x cubed? Well, if you plug in a positive value, then you're going to get a positive value back. If you plug in a negative value, you're going to get the exact same thing except negative, meaning that f of x, but multiplied by a negative, will be equal to f of negative x. Right? Again, if you were to plug in positive 2 to x cubed, you get 8. Well, that's not quite exactly equal to x cubed when you plug in negative 2, but it would be equal if you multiplied it by a negative, right? Negative 8 would be equal to negative 8. And this has to be true for all x values. In other words, there is symmetry about the origin. So if you were to rotate 180 degrees about the origin, you would get the same exact function. That's what symmetry means. Again, a function can be neither even or odd. So if you were to go through and try defining that it was an even function and try to prove that it was an odd function, and you found that neither worked, you would say that it is neither even nor odd. So what happens if we're asked to show whether a function is even or odd or neither? How do we do that? Well, what we're going to do is we're going to look to the definition. So we know if we are looking to show that it's an even function, we want to show that if you plug in some value x and you plug in its opposite, you're going to end up with the exact same value. If we want to show that it's an odd function, what we do is we'd plug in a value x, multiply by a negative, and see if that was the same as plugging in the value negative x. And this is actually easier than it might sound, and so let's go take a look at an example to kind of make this concrete. So here's a problem. Is f of x, which is equal to x squared plus 1, even, odd, or neither? So here's what I want you to do. Before we actually go through and prove it algebraically, I want you to sketch a graph of this function. So you should be able to sketch it by hand, and if you need to check Wolfram alpha, check Wolfram alpha. And then just based on the sketch of the graph, decide whether you think it's even, odd, or neither, and then try and use the definition to show that it's even, odd, or neither. And then press play and we'll take a look. Okay, so I sketched a graph, and my sketching skills are not exactly perfect, but we know that this is just the parent function x squared translated up 1 unit, so this is what we get. And if I just look at this, what kind of symmetry do we notice? Well, we notice that it's symmetric about the y-axis, right? So we're going to say it's even, but how could we prove this algebraically? Remember, to prove that something is even, we need to show that f of x is equal to f of negative x for all x values. To show that it's odd, we need to show that negative f of x is equal to f of negative x. So how would we actually do this? How would we show that, hey, if I plug in some value x, it's equal to what I'd get if I plug in its opposite value? Well, what if we tried just plugging in like one x value? For example, like what if you plugged in 2 and negative 2? Well, let's try that. So f of 2 is going to be 2 squared plus 1, which is 5. F of negative 2 is going to be equal to negative 2 squared plus 1, which also equals 5. So for at least 2 and negative 2, this is the case, right? If I plug in 2 and then I plug in its opposite, I'm going to get the same value. But does that show that it's the case for all x values? And sadly, no, it doesn't. And would this be an efficient method to go about showing that this is the case for every single possible value x? No, you'd be here forever, right? There's infinitely many possibilities, and so you'd have to just do this over and over and over again. So how could we do this so that instead of just using 2 and negative 2, we're actually showing that, hey, it doesn't matter what value you plug in. If you plug in its opposite, you're going to get the same thing. Well, let's do exactly that. Instead of plugging in 2 and negative 2, let's just use a generic value. In other words, let's just use x and negative x. So what's f of x? Well, f of x is pretty simple, right? I plug x in, I get x squared plus 1. Okay, what's f of negative x? Well, f of negative x, well, we have to plug in negative x here. So we have negative x squared plus 1. Okay, well, what's negative x times negative x? A negative times a negative is always a positive, so that's just going to be x squared. So I can simplify this to just be x squared plus 1. And that, of course, shows exactly what we were looking for, right? If I plug in some value x, I get x squared plus 1. If I plug in its opposite, I'm still going to get x squared plus 1. So f of x equals f of negative x. Therefore, f of x is even. And this shows it for every single possible value of x. So while this over here is good to give us an idea, right? Plugging in 2 and negative 2 helps us kind of take a look and make a decision. It doesn't actually prove it. So in order to prove it, we want to actually show that f of x is equal to f of negative x. Okay, so what we do is we take a look at what's the definition of an even function, and then we look to show that if you take f of x and you take f of negative x, which is what we did right here, that those are actually the same thing, that they're equal. Okay, so let's go ahead and try this with one more. Okay, here's a slightly more complex function. Is f of x, which is equal to 2 times x cubed minus x squared, even, odd, or neither? Okay, so let's just think about what would be really helpful here. Well, if we look at a graph, that would be really helpful, right? But do you want to try sketching this by hand? Imagine you didn't have Wolfram Alpha right next to you. Probably not, right? So in this case, the graphical representation is going to be a slower way. We actually want to use just the algebraic check. So let's remind ourselves again. What will it mean to be even? What does it mean for a function to be odd? Make sure you remember those definitions. Go ahead and annotate just like I did on the previous question, and then we'll go ahead and take a look. So an even function is when f of x is equal to f of negative x. And an odd function is when negative f of x is equal to f of negative x. Okay, well, let's try these out. So let's first check if it's even. So remember, to check if it's even, I need to find f of x and f of negative x. F of x is really simple. I'm just plugging in x. 2x cubed minus x squared. All right, what about f of negative x? Well, let's try it out. You have 2 times negative x cubed minus negative x squared. And notice that we can simplify this a little bit. Since this is a negative value, right, negative x cubed, what you can do is you can multiply this by itself 3 times. And so a negative times a negative times a negative is going to be a negative. So you're actually going to get whatever x cubed is, but the negative value of it. So you can rewrite this with the negative out front. It's going to be negative 2x cubed. And remember, that's because a negative times a negative times a negative will always be a negative. So I'm going to get the x cubed value except the negative version of it. Now I have minus, and negative x squared, just as we saw previously, a negative times a negative is a positive. So this is going to be the same as x squared. Well, is this the same as this? Certainly not, right? This value here is negative 2x cubed, and this value over here is 2x cubed. So those are not going to be equal, right? Because x is the same, so when you cube x, multiply it by 2, and then multiply it by a negative, that'll be different than when you cube x and then just multiply it by 2. So it's not even. Okay, let's try odd. So to show something's odd, we need to show that negative f of x is going to be equal to f of negative x. So let's try negative f of x first. So that means we're going to multiply whatever f of x is by a negative value. Okay, well, we distribute the negative in, and we're going to get negative 2x cubed plus x squared. Okay, and we need to show that this is equal to f of negative x. Okay, well, we actually already did this, right? We did this over here. That just ended up being negative 2x cubed minus x squared. And real quickly, I just want to talk about why it is, again, that a negative x cubed can be rewritten with the negative out front. Imagine you had the number negative 3. Negative 3 cubed is just going to be negative 27. 27 is just 3 cubed. So let me write this over here. If I had negative 3 cubed, right, 3 times 3 times 3 is 27. But because there's a negative here, it's going to be negative 27. Well, that just means I have negative, and then whatever 3 is cubed, right? So I can write the negative out front and then just cube 3. So again, I have negative 2x cubed minus x squared. Well, are these two the same? These first two terms are, but then I am adding x squared and then subtracting x squared. And so certainly those values won't be the same. So this won't be odd. In fact, since it's neither even nor odd, this is what we call a neither. Right? Neither even nor odd. Okay? Okay? So it's not going to be symmetric about the y-axis, and it's not going to be symmetric about the x-axis. All right, I'm going to give you one more, actually two more, sorry, for you to try to show whether they're even, odd, or neither. All right, go ahead and find the solutions to each of these. So you are determining if each function is even, odd, or neither. We just did a couple of examples together, and so all the steps should be very clear, right? You know what it means to be even, what it means to be odd, and so for each of these functions you can check, just like we did previously, whether the function is even or odd, and if it's neither, then it's neither. Once you've proved it algebraically, go ahead and sketch a graph. You can go on Wolfram Alpha to sketch a graph and see if the graph and the symmetry of the graph agrees with what you found algebraically. If you're a little stuck, one trick that I like to do is like we did on the first example. I like to plug in a nice easy value like 2 and -2. And that gives me a hint, right? If I plug in 2 and -2 and I find that they're the same value, then I'm like, okay, maybe this could be even. Let me try. If I plug in 2 and -2 and I get the opposite values, then I'm saying to myself, oh, okay, that makes it sound like it could be odd, right? Because the negative value is the opposite of when I plug in the positive value. And so you can try that out if you're a little stuck, but you should be perfectly capable of going all the way through. Just takes a little bit of hard work.